In the last class, we looked at how to set up an NMR experiment, and we looked at the different sample preparation steps and how the sample should be prepared and what should be the typical concentration. So today we will continue with that, and we will see the different steps which we are required to set up an NMR experiment. So once you prepare a sample, once the sample is prepared, then we have to insert the sample in the magnet, and this is shown here in this slide. You can see that what typically is done is, the first you take the sample in a clean dry NMR tube, and this is shown on the right side. This is typically the picture of an NMR tube. Here it consists of a 5 mm diameter glass tube, and this is 5 mm diameter. It can also be smaller, 3 mm, and depends on the spectrometer. The standard overall everywhere is basically using a 5 mm NMR tube, and the sample volume which is shown here, the sample is actually about 600 microliters. So this is the height of the sample volume. This is typically about 1 inch, 1.5 or 2 inches, not more than that, about 1.5. And so what is done is, this NMR tube is now taken and inserted into the magnet. So this is shown in the picture here. So this is the magnet, and the sample goes right at the top. So you have to put it in what is called a spinner. A spinner is something which holds the magnet, so holds the tube. So the tube is not directly put as such. We put it in a spinner, and the spinner along with that is inserted into the magnet at the top. And then once the sample is inserted and it is sitting inside, so typically the sample will come all the way down here, somewhere at the center of the magnet, that is the probe. So we are looking in the middle of the magnet is, remember, wide is a bore, is an open bore, and that is where we put the probe, and the sample goes and sit inside the probe, and then it goes somewhere in the middle of the magnet. So then after the sample is put, the temperature of the system is set to the desired value. So this is, the temperature is typically controlled in NMR by air. So what is done is, let us say you want to set a temperature to 25 degrees Celsius, you pass cool air. So the air will be cooler than 25, it will be about 15 to 20 degrees, and this cooling is done by like a refrigerator which is kept down on the floor, and the cool air is then heated to the desired value. So if you want to go to 25 degrees or 30 degrees, you heat that air, and the air is circulated. So typically if you look at this picture here, this is the sample tube, and the air is given from bottom, and there is a thermocouple, which sits and monitors the temperature of the sample. But remember, this is the temperature what you set is not the temperature actually inside the sample. That is difficult to monitor because there is no thermometer or a thermocouple possible to insert into the sample, and therefore what you are actually measuring is the desired temperature around the sample. To measure the exact temperature inside the sample, there are different temperature calibration methods which are used. We will not go into detail for those methods. Typically a standard sample like methanol is used, and in the methanol you get two chemical shift, two peaks, one corresponding to the methyl and other corresponding to the OH. So the difference in the ppm value between the two peaks is related to the temperature. So by recording a methanol spectrum, one can actually calibrate the temperature. So the temperature is a very important parameter in NMR experiments, because this is a sample dependent and this is a experiment dependent parameter. So one has to make sure that the temperature what you need is actually what is inside the sample. So temperature calibration forms a very important step in setting up the NMR experiment. Then once you put the sample and set the temperature, the next three things are to be done. One is what is called locking, and locking is something which we saw in the last class, and where we said that you need to monitor the deuterium frequency. The reason being that the magnet continuously drifts. We use the word drift, which means the magnetic field is lost, and because of this drift we have to correct it so that it does not affect the spectrum, and that correction is carried out by a small current which is applied in a coil, which corrects the current adds to the frequency, and the amount of frequency to be added is based on the deuterium signal, and this is silently carried out in the background, and we will never come to know that there is a deuterium spectrum being required but it is definitely required for locking, and therefore your solvent or sample should have a small amount of deuterium. Typically the amount of deuterium is used is about 5% if the solvent is protonated. But you can also use deuterated solvents like CdCl3, CD3OD and deuterated water D2O, where you do not have to add, I mean the deuterium is already present in the solvent. But in case you are working with protonated solvents such as H2O, there you have to add a small percentage of deuterium for locking. So, once the locking is done, as it is said here, it is mostly automated, and then you go to the next part where you actually shim the magnet. The shim, basically the word has a historical origin. It basically means that you want to homogenize the magnets, homogenize the magnetic field across the sample. So, if you look at this picture again here of the NMR tube, typically what happens is this is a sample, but all the molecules of this sample do not experience the same magnetic field. That is because the magnetic field may not be homogeneous or same across the whole sample. So, to homogenize, to equalize that magnetic field across the whole sample, we need to do this process called shimming. So, we have seen this in the previous class where we saw that what homogeneity, how it is equalized, how it results in a very sharp line. So, the sharper the line, the more is the resolution in NMR. So, one of the main requirement in NMR is the line should not be broad. So, and why it is broad? Many a times it is broad because the magnetic field B0 is not homogeneous, and therefore one has to do shimming. So, shimming again in today's spectrometers is done primarily in a very automated manner. So, this is simple command based operation, and within few minutes. So, this operation takes about few minutes, few seconds, this operation takes another minute. So, within very quickly you can shim and tune lock the system. The next important thing is to tune the spectrometer to this frequency. So, this is something analogous to what I was telling the other day, that suppose you want to tune a radio. So, if you are listening to a radio and you have different FM channels and you want to tune to a particular channel which of your interest. So, you turn the knob and the knob basically tunes the frequency for a best reception to the frequency which you desire. So, if you slightly turn the knob more or less, you will see the blurring of the sound. So, only at the exact frequency of the radio channel we get the best reception and audio quality. The same thing is applicable to NMR, that at the best frequency what NMR, the frequency of a spectrometer, you have to tune exactly to the frequency so that the maximum signal to noise you can obtain, the maximum signal can be obtained. Otherwise, the signal to noise deteriorates very rapidly. So, tuning is again a very important, similar to what is done in locking and shimming. Nowadays, this is also automated. So, this whole operation of locking, shimming, tuning typically takes about 5 minutes to 10 minutes, and after you put the sample, within that period of time the sample is now stabilized to the temperature, and we are ready to go to the next step, that is recording the spectrum. So, the first thing, so when you want to record a spectrum, so remember in NMR proton, typically the scale for many molecules, almost all the molecules, you will see that the chemical shifts always will come somewhere between 0 ppm to around 10 ppm. So, this is typically the range for all the many molecules in chemistry and biology. So, what is done is you have to set what is called a center frequency. So, the offset. So, this is a technical jargon which is used in NMR for recording a NMR spectrum. So, we say that what is the offset value. So, the offset value basically represents the center of the spectrum. So, it is a very simple idea, the center is around 5 ppm. So, what typically is done practically is that we take the water, suppose let us say you are recording a sample in D2O or H2O, then the H2O signal comes somewhere around 4.7 at room temperature. So, you take that as a center. So, center is taken as a water frequency, but if you are doing it in some other solvent like in CDCl3 which is shown here, in that case you take the center to be around 5 ppm. So, once the center is set to 5 ppm, you roughly set the whole spectral width. So, this is what you have to do the next, the spectral width, there is a range of chemical shifts. So, here is about 1 to 10 ppm. So, what you can do is take the center as 5 ppm and then take the range of chemical shifts as 10 ppm, and then you can record the spectrum. So, typically for a small molecule like this you will see the different peaks. and we will see later how do we interpret this peak pattern, but this is just to get you an idea that the peaks come somewhere like this. And if you go to a little larger molecules like biomolecules, proteins, it is more complicated looking, but again you see here the peaks are typically coming somewhere between 0 to 10. A slightly side deviations will be there, but more or less the range is 10. So, in the beginning when you do not know the chemical shift range, the spectral width of your sample, you can choose about 15 ppm. So, 15 ppm will cover surely the full range normally observed in molecules, and then once you have recorded data with 15 ppm, you can shorten the spectral width to your desired value and avoid the extra regions where there is noise. So, this is how typically the spectrum is recorded, and one of the major things in NMR is what is called solvent separation. When we go to the advanced the applications of NMR in this course, we will see how what are the different techniques for solvent separation, and this is a very important area of research. Many papers are published in literature for achieving a good solvent separation. Now, the question is, why do we need solvent separation? You can consider this in the following way. Suppose let us say you have a water sample, ignore for the moment that we have deuterated chloroform. Let us say you have a sample dissolved in water, H2O. Now, what is the concentration of H2O? Concentration of H2O, remember, is 55 molar. That means if you take a glass of water, you are having 55 moles of the protein in 1 liter. That is 55 moles of the water in 1 liter. So, water has a concentration of 55 molar, but typically the concentration of our sample, the compound we take, is about the order of millimolar. You may take, let us say, 10 milligram, 20 milligram in dissolved in half an ml, 500 microliters, and that if you calculate, you may get around typically about a millimolar, or let us say 5 millimolar. So, now if you compare 5 millimolar with 55 molar, there is a factor of 10 to the power 5 difference. That means the water is 10 to the power 5 1 lakh times stronger compared to the signal of their compound. So, this is called a dynamic range problem. So, dynamic range problems means that you have a huge range of concentration in your sample. One molecule which is your compound has having a concentration of let us say 5 millimolar, but in the same NMR tube you have water which is sitting at the concentration of 55 molar, which is 10 to the power 5 times. So, when you have this kind of a huge difference, NMR spectrometer cannot work properly. It fails to record a good signal spectrum for your sample if the solvent is at a huge concentration. So, therefore, it is very important to suppress the solvent peak, so that when if you suppress the solvent peak all the way from 10 to the power 5, let us say to 10 to the power 1, means instead of 10 to the power 5 times larger than the compound, suppose it is 10 times larger, then it is coming within the range at which the two molecules, that is water and your compound, have the similar order of concentration. Okay. So, it is never possible to suppress a solvent 100%, that is for practical reasons which we will see in the advanced part, but it is not possible to suppress water 100% completely. So, therefore, at least if you can reduce it by a factor of 10,000, then you come down to the level where it is similar signal to noise compared to your compound, and that process of suppressing this peak is called as solvent suppression. And there are, as I said, there are varieties of methods available in literature to suppress the solvent, and we will see some of them as we move along. So, once the solvent suppression is taken place, the next step is to calibrate the pulse width. Typically what happens is we actually do the solvent suppression after doing the pulse width calibration. So, what is a pulse width calibration, which is shown here? So, what we are trying to do is, remember I showed you a pulse sequence of our 1D experiment. 1D experiment consists of a single pulse and which is typically microseconds, and then immediately after the pulse you start recording or acquiring or physically detecting the signal, and that is called a FID. So, this pulse which generates the FID has to be well calibrated, and when we say calibration, what it means, it should be a 90-degree pulse. So, if you remember back the picture, remember a 90-degree pulse brings a magnetization from this z axis. If you apply, let us say, along x axis, suppose this pulse is applied, let us say, along x axis, then it will come to y axis. This red color vector will rotate by 90 degrees and it will come to the y. If you apply along y axis the pulse, it will go to the x axis. So, it will always go to the perpendicular to where the pulse is applied. So, let us assume that let us say this pulse is applied along x direction. So, we apply this pulse. Remember, pulse is nothing but a magnetic field, a second magnetic field which is applied perpendicular to the main magnetic field. So, main magnetic field is in this direction and we are applying a perpendicular magnetic field which is much smaller. It is a very small magnetic field of the order of kilohertz compared to what you get here. This is megahertz. So, this kilohertz magnetic field we apply perpendicular, the magnetization will rotate and will come to this direction by 90 degrees. Now, when it comes to the 90 degrees and suppose you keep a detector here where the arrow is pointing now, at that point the signal will be maximum, because the detector will get the maximum vector signal pointing towards in that direction. Okay. So, therefore, it is important to calibrate the pulse width, that is how long does the pulse take to bring the magnetization from z axis to this y axis by 90 degrees. So, the pulse width means how long does the pulse take to bring the magnetization from z axis by 90 degrees to y axis. So, that is very important, because if I do not calibrate this properly, suppose let us say it is not 90 degree, I make it 70 degrees, and in that case this red color magnetization would not have come 100%, it would have been sitting somewhere in this direction, and then the component of that along this direction is what will be detected, because detector, remember, only detects what is coming in this line, it does not look at any other direction. So, if the component of this vector along this line is reduced, then your signal will be reduced. Okay. So, therefore, it is important to determine 90 degree, and that is practically what is done, that instead of recording a 90 degree we measure a 360 degree. So, if you look at this here picture, if I record a 90 degree, the magnetization comes here, which is a maximum positive signal which I mentioned. Now, but if you do a 360 degree rotation, the whole magnetization has come back full circle and is back to z axis. So, obviously, you do not expect any signal at after a 360 degree pulse. Why? Because the signal is exactly along z back to z, and therefore, its component along the y where the detector is kept is 0. So, a simple component analysis, if you look at the component of this is 0, therefore, the signal is 0 along this axis and the detector cannot detect any signal. So, by recording the signal at different angles, I can figure out I get the maximum signal and where I get the minimum signal, and that will give me the two different values, and I can figure out the exact 90 degree pulse value from this exercise. So, this exercise is done for every sample whenever you put it in the magnet. Again, this is done nowadays in an automated manner, therefore, it takes about 5 minutes to calibrate, to find out the exact 90 degree pulse. So, we can go on to this is what is shown here, how it is recorded. So, typically what is done is that to calibrate a 360 degree pulse, we go like this, we start from 0 degrees, go to 90 degrees, go to again 180 degrees, is 0, okay. And then if you look back in this slide, see, remember 0 is there is no signal at 0 because the component along y is 0. Then if you do 90 degrees, it is maximum. If I go to 180 degrees, it is again 0, because 180 degree is perpendicular, is exactly perpendicular to this y axis. So, again the detectors cannot receive any signal because the component of this vector along this direction is 0. Then it goes to 270 degrees, which is here, and then 270 degrees again it is perpendicular to y, you will not get, but if it is detector is along it goes from here to here. So, first 90 degree comes here, then 180 is here, then it goes back to 270, which is in the opposite direction. So, when the vector, this red color vector is sitting in this direction along this minus y, then the signal is negative, because the detector is, remember, along this line. So, anything which comes along this line, it can detect as a signal. So, whatever the component is along this side will be negative. When you go back to 360, it is back to 0, because again there is no signal along y. So, this is what is shown here, that when you start recording an NMR spectrum, you will first get nothing, 0 because of 0 degrees, then next slowly the signal increases, this corresponds to 90 degrees maximum, comes down, it becomes 0 at 180 degrees, then again goes to negative, comes back, and so on so forth. So, this is how the pulse widths are calibrated. For example, if I know the 0 degree value is this much, I just take it by half. I mean 0 degree means 180 degrees is here, then I take it by half, and that half will give me the 90 degree pulse width. So, typically the value of pulse widths in NMR range from about 10 microseconds to 20 microseconds. So, that is typically the range we see in NMR. In fact, pulse width is a very important parameter to figure out if everything is right with the sample and the system. So, it is like when you go to a doctor, he looks at the pulse beat of a patient, and based on that he can figure out if the person is having a particular problem, ailment or not. Similarly, an NMR expert, by looking at the pulse width we get by this exercise, he can figure out if there is a problem. So, let us say the sample, if you get say about 20 microseconds value instead of 10, then that means there is something wrong. So, there could be either the sample has lot of salt in it. If you have a very salty samples, remember in biomolecules you have to always add some salt to keep the molecule stable, and that salt increases the value of pulse width because of certain effects we will see later if time permits, but mainly it is because of this loss in resistance and so on. So, therefore, if there is a higher salt in the sample, it causes a longer pulse width, and that causes a loss in the signal to noise. Or it could be that the spectrometer is having a problem, the transmitter which provides the RF signal, the transmitter has gone bad, and therefore, it is not able to provide enough power. So, if the power is not enough, what it means is that the pulse width goes up. So, and so on and so forth. So, as for an expert NMR, a pulse width is a very important number which gives you a lot of insight or idea about the system of the spectrometer. So, this is what is shown here, that there are different reasons why the pulse width can go wrong, and one of the thing is, let us say if you change the temperature, if you are at a very high temperature low, the spectrometer may not give the exact pulse width what you expect. It may be that your tuning was wrong, you did not tune the spectrometer. So, remember in the beginning I said this is an automated step, but sometimes one may forget to tune the spectrometer, and that will be reflected in the pulse width of the sample. It could be that the salt, it has a lot of salt is there in the sample, and that can cause an increase in the pulse width, or finally as I was saying that it could be a hardware problem, that the transmitters or amplifier are not able to provide the enough power to the system to get a very accurate pulse width value. So, these are the different reasons why the pulse widths can go wrong. So, once the pulse width is set properly, the next step is the set up what is called as a spectral width. So, these are the parameters. So, we are going basically through this exercise because the idea is that when you record an NMR spectrum, one should be aware of what are the different parameters which one should use, because many a times what happens is that it is all automatically set, and the users or the students do not get an idea about what is happening behind the screen. So, this the whole thing we are going through now is basically to give an idea that what is involved in recording data, but as I said, as a user you may not even worry about all this. In the end you may just record whatever is the standard default values, but it is important to understand and know that what is goes on behind recording a spectrum. So, the next parameter we come to this is spectral width. Spectral width is basically the range of chemical shifts where you expect to see your peaks. For example, as I said, in a molecule typically we expect somewhere between 0 to 10 ppm. So, 0 to 15 ppm. So, that is the typical value we set, but now the question arises is, suppose I make a mistake, I do not set the spectral width properly, or we also use the word spectral window, I do not correctly set it, what happens to the spectrum? So, what happens is the following. What happens is, let us say that you have a peak sitting outside the window, and let us say you gave this window to the spectrometer to record data, but by mistake or by chance which you did not realize, there may be a peak sitting outside this window. What happens to that peak? Typically what happens is, if it is too much away from this window, it is simply cut out by electronic devices called filters. The filters will just set up a range that it will chop any signal out of this on this side. So, what happens is, most of the time you will just not see this peak at all. But in NMR there is a fundamental thing what happens sometimes, you will see this more in 2D NMR, that if you do not set the spectral width correctly, this peak which was expected to be seen outside this window comes and appears in the spectrum at this position. So, what is this position? This is exactly this distance. So, you take this distance from here as shown by this arrow, you take this distance, and at the same side this distance it will come as a mirror image. So, this is like a reflection, and this point, this is called aliasing. This is a very standard terminology used in signal processing. It says the signal is got aliased, or in other words we use the word folded. It is like folding. So, imagine that, let us say you fold around this axis, this is a mirror image, these peaks will come here. So, you may see a very spurious peak here, and you will not know whether that is coming from the actual sample or is it a folded peak. So, that you will only come to know if you open the spectral width. So, let us say you expand the spectral width to now include this peak, then this peak will disappear and the actual peak at the real position will appear. So, one of the ways to find out if the peak has got folded or not, or aliased or not, is to expand the spectral width. So, this is what typically we do. We start from a very large spectral window in the beginning and just scan the region where the peak should come, and then a second time we record again the data, but with a shorter spectral width which will exactly cover all the peaks. So, the first step is done to get the idea about where the peaks are there, and after that a second experiment is repeated with everything the same sample, all the same setup, except that the spectral width is then narrowed down to the range which you need for actual data. So, therefore, if you forget to do this expanded spectral width, if you end up folding a peak, that peak will appear in this side. So, this is called aliasing. So, commonly, in fact, in multi-dimensional NMR, when we see in 2D NMR, we purposely have to do this sometimes, because reducing a spectral width helps you to save time, and thus those details we will see that later. But the spectral width, and then when you deliberately reduce the spectral width and you miss a peak, that peak does not go away, it comes back, but it comes back in a aliased manner, and there are different ways to figure out whether this particular peak is aliased or not. So, it does not matter so much if it is folded, provided you know that it is folded. So, as long as you know that this is a folded peak, you do not care, because you can calculate the real value by simply looking the distance from here and taking it on this side. So, that will be the chemical shift actual value. So, this is the problem when you do not set the spectral width correctly. Another next important parameter to set up in a 1D NMR experiment is what is called relaxation delay. So, if you can recollect, in the last class we showed you the pulse sequence. A pulse sequence is basically a diagram, a picture of how the different pulses are executed in an NMR experiment, and one of the first it consists of, pulse sequence basically consists of pulses and delays. So, RF pulses and delays. So, the first delay is called relaxation delay. It is just simply a delay where nothing happens, it just a spectrometer is sitting silent during this portion of time. And what is this period, reason why is it required? This is required, remember, to sufficiently bring the magnetization back to equilibrium, because when we apply this pulse, the FID is like this and the signal has come to the XY plane. During this period, the signal has come from Z axis to the X or Y axis. So, after this period is over, if I want to repeat this, if I want to repeat this whole process, I cannot start from here, because the signal is lying along X and Y axis. I have to allow sufficient time for the whole signal to come back to the Z axis before I apply a pulse. So, to allow that duration for the whole for the magnetization to come back to Z axis, we take the sequence to this period, means we give a delay between the next pulse. So, the delay is applied between two pulses. After the detection is over, we use the word relaxation delay. So, relaxation delay is now typically as a ideally is something like 5 times the T1 value. So, T1 value is something which you may not know a priori of your sample, but if you have a rough idea, if you know the molecule size and so on, which is shown here, we will see this part again later when we go to the relaxation topic, but T1 value can be roughly estimated for a given molecule based on the size and temperature. So, based on that value you have to multiply it by 5 times, and that is the value ideally, remember the word ideally, it is required. but practically that becomes not a very good solution, because let us say the T1 of your sample is 10 seconds. So, 10 times 5 is 50 seconds, that is 1 minute. So, the 1 minute of a delay is too long, because let us say you want to repeat this cycle 1000 times, because your sample may be having a very low concentration. So, if you want to repeat this cycle 1000 times, you have to multiply 1000 into 1 minute. So, 1000 minutes, and 1000 minutes is a huge time to record a 1D spectrum. So, therefore, what typically is done is that you do not take 5 times, roughly you take about 1.5 times or 1.25 times T1. So, this mathematically we can show it, although we do not show it in this course, but mathematically you can show that this is an optimal delay value which one can choose to get the best signal to noise, means the trade off between signal and time. Remember, time is also signal to noise. We saw this in the last class, that the longer the time you record, the longer the time means longer the number of scans, more the number of scans you use, better is your signal to noise. But if I have to give a long delay between scans, then my time goes up very tremendously, but my signal to noise is not improved, because this delay, remember, is doing nothing, just idle time. So, therefore, to compromise, we reduce this time by to 1.25, but time is also reduced. So, you can record with more scans now. So, you can see that on one hand you lose signal because of reducing this delay, but on the other hand you gain it because of more scans. So, overall optimally mathematically it has been shown that this is the ideal time. So, if let us say your T1 value is 1 second or let us say 10 seconds, you just need to use about 12 seconds. So, it brings down the time by a factor of 5 from 60 seconds to 12 seconds. So, this is practically the value which is used in many experiments. So, typically the relaxation delay is in the range of 1 to 10 seconds for organic molecules. When you go to larger biomolecules, there the relaxation delay can be further reduced, because biomolecules have a very short T1, means the value of the T1 is less compared to the value of T1 for an organic molecule. And why is that so? That comes from this whole theory of T1 relaxation, which we will see at a later point. So, this is what is shown here, that T1 decreases with the size of the protein, so increases the size of the protein, and the T1 decreases with size of the molecule. So, therefore, T1 is a parameter which depends on the molecule, and once you have a rough idea, you have to use a correct relaxation delay between the scans. So, these are the few parameters which you have seen in the setting of the experiments. We will continue a little bit more on what are the other more parameters to be recorded or used in the next class.